have to describe this is general relativity and quantum mechanics. People are still trying to unify them. And so it is our hope that in the long run, our project has been scheduled. This is very ambitious, as we have said, and it is scheduled for the next 20 years. So we have planned it for 20 years research. So our hope is that by that time, perhaps we will have a better understanding of this fundamental phenomenon. Having said this, let me start with a very basic and very simple beginning. So, what is the process of printing? In some sense, it can be thought of as putting something somewhere in a definite way. So, in the basic simple example of which we can think of is by taking points, by putting points in a plane. So something is points, somewhere is the plane. Let us suppose we are considering the complex plane of complex numbers for definiteness. And so it is just a bunch of points. It can be modeled as a set of numbers with a geometrical interpretation or realization. So that means we have a set of things, the something, and we have a space, the somewhere. So what formally means putting something somewhere, in this case points in the plane. So it's just a map that has domain the set of points and codomain the complex numbers, which gives then a geometric realization to each number. So if we label the numbers 1, 2, 3, 4, etc., then G of any of such indexes, being a complex number, is its geometrical realization and gives the coordinates to that point. So that's for if we are concerned with printing points, that's it. We have solved the problem. But very soon we start to realize that, okay, but points are not so interesting. Perhaps we want to make them small dots, small circles, and so each point is carrying a size. All right, we can still make this into our model. We just equipped it with a parameter map, let us call it R, which associates to each index modeling a point a radius. And then we interpret it as a point at the center of a circle, and this is the new objects. Well, sooner or later, the points perhaps will try to differentiate from each other. And or even before that, instead of just one parameter as radius, we can instead of circles we can have squares, triangles, etc. So we better add more parameters in our model. So for that reason, we could have the number of sides of a polygon. So we still have a set A of indexes for our objects, namely points. We have the plane where we are trying to print them. We have this geometric realization map, G, associating to each point its specific coordinates in space, giving instructions where the points shall be printed. And then we have this space of parameters, a radius for each one of the dots, and the number of sides for each polygon. Now, if we allow a rotation of this regular polygonal shape, it is still possible to include into the model. So since we have a phase angle and an amplitude and the number of sides, so this can still be modeled as a parameter space. So I suppose you can see the cursor of my mouse. So I'm pointing now to this space C cross N. Is it visible?
Yes, yes.
Please. Okay.
Yes, it is.
Thank you. Well, but as I was saying, sooner or later, one point may try to differentiate from another one, and more complex shapes, or not all regular, can be considered. Let us say, for instance, suppose we have now, instead of a regular shape, we have some arbitrary shape. So at this stage, our model is no longer appropriate, or at least the information in the model can be the same, but we have to reinterpret it. And for that respect, we actually have to insert something new in the model. So in the sense that, okay, we can still have a set of indexes, like small dots, but now each small dot is just part of a component. So what we were previously considering one single point is now this shape figure. And it consists of small points. Okay, so this gives one more level of structure into our model. So how does it behave, or how does it handle this new information? Okay, we still have points. They are labeled as just indexes in this indexing set A. We continue to have this map G with the geometrical realization from our set of indexes into the complex plane. But if we stop here, what we will have is just a collection of points and no connection between them. Since we want to define this polygonal shape, what we do is we add to our model this map or endomap from A to A. I call it alpha. I'm not sure if it is visible. Maybe I can increase this. So this alpha, what it does is just ordering or giving a transition on the points. So it says that number 1 is connected to number 2. So you see here. So alpha is just a map, can be seen as a table. So for computational purposes, it is very convenient. So A is the elements of A are this column here, X, and the image of each point by this function alpha is represented in this table. So the number 1 goes to number 2, number 2 goes to number 3, number 3 goes to number 4, 4 goes to 5, 5 to 6, and 6 comes back to 1. Okay, this map alpha is called the transition map, and it allows to isolate components. So we can still have a bunch of points, arbitrary points, but instead of each one of them being the actual something that we are printing, it is only a part of something that we are printing. And this connection, this transition map, tells how many connected components will we have. All right. So now, because we can have more points and more connections between them, so we can have this this as a connected component, and then other connected components, and they are all described by this same model. All right. So this leads us to the definition of a complex link. So complex link or colored link is a mathematical structure consisting of a set A of indexes, an endomap alpha, which is a map from A to A, called the transition map, and a geometrical realization, G, from A into the complex numbers. And we will also allow for a projection map or a colored map, which will be, again, give the extra information of parametrizing each of these connected components. All right, let us see a more not so simple but still easy to handle example. Suppose we want to define these two curves, these two circumferences on the complex plane. So instead of saying that it is one point with the radius and another point with another radius, if we discretize this circumference as a collection of dots, then we can freely move these dots by changing its geometrical coordinates, but still keeping the same connection. And we have this extra expressibility in the information that we are printing. So this is just the formula for circular shifted one to the left. Here it is shifted one to the right. But so you see the map alpha. So let us consider a certain number n, make it double to have sufficiently many points, n points in one circle, n points in another circle. And now we are free to move these dots in space by changing its coordinates. So for instance, if instead of -1 here, if we change it to -1/2, and if instead of +1 here, we make it +1/2, then this figure changes into this one, and there will be intersections here. So these intersections, they give us the freedom, this transition map combined with the geometrical map gives us the freedom of changing what region we are considering. And moreover, this projection map identifies whether or not they are different components or they are the same component. For instance, this projection map says that if I project all these points on the left circle to 1 and the points on the right circle to 2, it tells me that in the second level of abstraction, let us say, I can think of all this information as just one point and all this information as just another point. Whereas if I change this map P and say that everything goes to 1, so all this part goes to 1 and all this part also goes to 1, so it would be 1, 1, then it tells me that I'm considering this whole structure as one item. Okay, so there is this this freedom, and this is important for the model. All right. Yeah. So here was the idea was to explain that. So for any arbitrary region in the complex plane, we can model it in this way, and actually change it and reinterpret it as different regions and subregions. So for instance, if 0 is for the outside region, 1 is this inner region, then we can have negative regions in the sense that if we see this as support layers, so let's say 0 is the ground layer, so 1 is one layer above ground, and -1 is one layer below ground level. And there are some algorithms, some techniques that we have developed to handle the information in this way. So Right. So the idea here is that there is. Let me quickly skip this one and then come back. This notion of complex link can be used via the concept of winding number adapted to this concept to handle morphological operations in the complex plane. Let me just quickly go through this and say, okay, here is the general definition. So we'll have a set of indexes. There is nothing special about the complex plane. We can have any space. So let's say Rn. And even as I will mention this in the end of the talk, there is actually nothing special about Rn. And if we try to model the physical world, we very soon will move to other kind of Riemannian spaces, in which between 2 points, instead of linking them with a straight arrow, we will connect them with a geodesic path. And the geodesic path will depend on the metric, and the metric can be seen as the Einstein metric from general relativity. So this is how we currently perceive things. And moreover, the act of printing something, in the sense that putting some creating matter, will have the effect of changing the metric. So everything has to be connected in this ground. So the expressiveness of this structure can be seen as follows. We interpret the elements in this set A, which are just indexes, say number 1, number 2, etc., as not only vertices or points, but also the arrows themselves. And then this map G, making the geometric realization, together with this map, the transition map, allows us to interpret each little a in A as an arrow. So going from G of A and ending at G of phi of A. And moreover, if we continuously apply the transition map, we can take the full orbit of an element and arrive at its connected component by computing all its orbit. Now, this is important. This connection is important, and it gives this general notion of that we call multi-link. So a multi-link is a generalization of this idea. We can have several transition maps. Each transition maps gives a kind of independent direction at which we can take the orbits of an element. It has a geometric realization into some space. So this space can be different from one application to another. And it has this projection maps giving parameters, kind of parameters to each element. So now I will go back a little bit so that I would like to invite Miguel Galbut to actually show us the software that we have developed so far for temperature, which is also related with the two talks of João Pinheiro and Tiago Santos. And okay, once again, the idea is if we discretize the model for the heat equation into the structure of a multi-link, we end up with so each point in our domain has a geometrical interpretation. If it is conveniently modeled in three-dimensional space, we will have 6 transition maps, one for each possible direction with the orientation in space. So can move forward, backward, left, right, up, and down. And these 6 directions allow us to encompass the heat equation into a formalism which is then the same that we will use for the universe, for the concept of the universal printer. So Miguel, if you are kind enough, please show us the simulation. I will stop sharing my screen and allow you to show your screen.
Yes, I'm waiting for you to stop sharing.
So I have to stop. Do I have to do something? Okay, Tomas is taking care of.
No,
Yes.
I think.
Please,
Okay.
Miguel.
All right. So I'm just going to show you some of the videos of our simulations. So this is the simulation of I showed you a few frames before. Simulation of a filament with some width being extruded on a two-dimensional domain. The filament is extruded at the temperature of 100 degrees Celsius, I think. And so this domain is bounded by a material that acts as a sink, so it absorbs it flowing to outside the domain, and overlaid is the gradient of the temperature. And so this is 128 by 128 points. And well, this is a bit long simulation, but simulating about 10 minutes. Now this is a simulation with a different toolpath. In this case, it is a single element, single grid cell with filament, and it is being deposited in a spiral trajectory starting at the center here. This is just to show the flexibility of the algorithm to handle different toolpath simulations. And here we have identical one, but now we are doing a spiral inwards. So the cooling is totally different, of course. So it's interesting that we can simulate the different effects of these options. And finally, we have a more traditional scanning, like, for instance, we could have in SLM with, say, a laser that is hitting the material, a bed, a powder bed. In these simulations, the temperature is in arbitrary units. So and well, that's it. Oh, it's looping.
Okay. Thank you very much, Miguel. But there's still one more.
No.
Okay.
I finished.
Okay, so I continue sharing my screen. All right. So this was to show that actually we are now capable of using this model, this multi-link structure, and it can actually be so the implementation is the same regardless of the interpretation that we make to it, that we do to it. So in this case, the heat equation has been used, but it only uses the model, the base model of a multi-link. So if we try to simulate other physical characteristics, the only effect that it will have is to change the equation. So for instance, we could simulate fluid dynamics by just inserting here the Navier-Stokes equation or any other physical interpretation that we make to this. And still the model is the same. It's always being the same structure. So I had prepared some things here which were concerned with some other further examples of this multi-link, this notion of multi-link, but perhaps I will not take too much time. So just very quickly, a triangulation is can be mathematically abstracted as a collection of vertices V and triangles T, together with with the property that a triangle has these three vertices, vertex A, B, and C, and then it is realized geometrically in this way. And what happens is that even this notion of a triangulation can be transformed into a multi-link, in the sense that instead of triangles, we will have edges, but each edge is duplicated because it belongs to two triangles. And with these two transition maps, satisfying these mathematical conditions, this fully characterize, so this is a mathematical result, that a structure of this shape comes from a triangle if and only if there exists an equivalent way of seeing it as a multi-link, namely with these two transition maps, satisfying these conditions. And so this is actually a very powerful tool and expressive, so that instead of a triangulation, we can work with square links, double links, etc. Just give you the idea, but not entering into much details. For instance, a tetrahedron in this language is modeled in this way, where what you see here is that so a tetrahedron so as a geometrical figure consisting of four triangles connected together, where these four triangles, you can see one is this one, another one is this one, and the outside one is actually being expanded with also its edges and vertices. So each edge of the tetrahedron is actually this rectangular shape here. So now what this allows us is that when offsetting the structure, we have the expressiveness of all its geometry, in the sense that an edge is not really just a straight line. It has some extra structure, and this extra structure in this case is this square, so that the cycle alpha beta is the edge in one direction, and this alpha beta to the other side is the edge with the other direction. And this has some interesting consequences algorithmically, but I will not give too much details on here. Also, a cubic link. In this case, we have 3 transition maps, one for each transition, one for each direction in space, and they have to satisfy certain conditions. So, in any case, we have this notion of link and multi-link appearing and appearing again and again and again with many applications. So we have actually developed this concept and generalized the notion of winding number to these structures with very nice results. So I will skip this is technical stuff, but again the same idea. So having a geometrical region, it with self-intersections, sometimes it's there is an ambiguity of which region are we considering? So which colored region are we considering? And the procedure of the winding number enables us to overcome this difficulty and actually extract morphological properties from the data. Okay, so this now is examples with technical details. I will skip them. The idea was to share the algorithms and the complexity of the procedures that are behind them. So very quickly, give an example so that you can have a flavor of what I am talking about. So with this procedure, we can actually distinguish from, say, these 2 regions. So this is the union of the 2 regions. This part is the intersection. This one is the symmetric difference, and this is A minus B. Now, with this tool, only changing the connection between the points, we move from one interpretation to another. All right. So, for instance, at this crossing section, if we coming from here and we continue to A, we have the original piece. Whereas if we, so for instance, coming from here, instead of continuing circle A, if at this intersection we change from A to B, and this is only it's doing only changing the indexes in this set according to the transition map alpha, we can actually get algorithms, procedures for these operations. Okay, with input data A and B, we form a link structure, and then specific instructions can give as output intersection, the difference, or the symmetric difference, or even the union. All right, so
you're in the last minute.
All right, yep, to finish and summing up, this is where so I have discussed about something, what about somewhere? So the something is this notion of multi-link. It is, we are happy with it, so it's a fine structure. Now, what about somewhere? In the end, we will be interested in generalizing to the universe itself, so that the ultimate printer is the universe itself. And in that sense, if a multi-link can model a planet, then a planet can be printed. And for that reason, the space, here it is the notion of a Mobius space, which is soon to appear in the print. And it has some axioms. This is actually joint work with George Fatil. And so that we have actually modeled with axiomatic algebraic structure the notion of a geodesic path. And then there is further examples to topology, but they are still work in progress. And I finish here. Thank you very much for your attention.
Thank you very much. So we have some time for questions or comments. Let me expand the people. If you'd like to raise your hand. I wonder if I could ask a question just to clarify the part that you talked about, which was the zigzag arrangement of the polymer and the thermal analysis. And you said that there was you could write this problem down in terms of the multi-link. And then when either you were describing it or when Miguel described it, you had a throwaway comment that this line has a certain thickness. But where does that appear in this description? Because so far you've been joining presumably infinitely small points in space that have no dimension with straight lines that have no dimension other than the length of it. And so where does the length of the strand come into this problem? Because otherwise you're simply describing the centroid of the printed filament.
So that is a very good question, yes, and it is interesting. It is important to clarify. So there is different ways to see it. So actually what Miguel showed is what we have so far, and in that simulation we are considering the space discretized in, let's say, square units. So each unit square is a point, and only the points are being connected. I mean, the points are squares, are like squares.
So they're not points.
So they are. It's the way it is implemented. This moment is like a square matrix, an array or a two-dimensional array of elements, and these elements are the points. But of course, they have size, shape, and structure, and this is made into the model. However, if we connect to the presentation of Tiago was working in one dimension, but this one dimension can be embedded in R3. So one dimension means one transition along one transition. What I think is important to clarify here is that the same point, when I say a point, I mean an index to something, putting something into somewhere.
But so it's not a point then. I think it's very misleading to describe it as a point. You're talking about an area or a volume.
No, but that's the whole point. It is a point
it's not a point in the conventional sense.
It is in the sense that it is the only thing that has geometrical coordinates associated to it. But then what the rest of the structure allows us to do is to interpret it in some sense. So for instance, if you remember my first slides, we had a point, but if I give a radius to it, I can consider it as a sphere. Okay, so it's all about the extra information that we have besides the geometry. These connections, they allow us to build an interpretation that we can transport to the simulation models. So for instance, just a very straightforward example. If you want to simulate the temperature on a linear piece of rod, a linear rod, then that's it. We will just have as many points as we want to discretize it, and the transition map says that one point is connected to the next one, and so on and so forth. But each point, if the rod is a cylindrical rod, then as a circle, as a cross-sectional shape, it has a volume, and etc., etc., etc. And all these are parameters. This is what I would like to add. I'm not sure if it fully answers what you were trying to understand, but I think it's what I want to say.
Okay, Thomas, you had a question.
No, I haven't. I was just applauding the presentation. It's a very good presentation. I don't have the technical skills to debate this.
Yes.
I'm sorry. Thank you.
Okay, I had one further question. I don't want to be the only person who's asking questions. I would think that all of these blank screens that just have the name on are actually asleep. That when you started with the definitions, I think you had points. Let's avoid the discussion of what a point is. And you said these are joined. These have a link. And you described it as I don't know whether you used the word, but a straight line. All of the figures you had straight lines. And I wondered why it was that restrictive. Because if you want to print anything, by doing this, you're limiting the specification to the number of points that you can place to define the curvature or the shape of this pathway. Whereas you could, for example, use other geometric line shapes, which would give a higher resolution of definition of the shape, which would fit in with the idea of being able to define anything. Whereas if you have a series of points, you're limited by the number of points that you place.
Yes.
And obviously, I know you might say we can have an infinite number of points, but you can't have an infinite number of points.
No.
The computer won't allow an infinite number of points.
That's right. It's part of the model. It has to be a finite number. It can be any number, but it has to be finite because the algorithms depend on that. But you see, we are assuming the universe is finite, and we have a finite number of particles. That's what we are assuming. It is true. So if our universe ends up being infinite, our model has to be changed.
I think if the universe is infinite, we all die. But is it possible to incorporate other shapes to the links?
Of course, the links are giving the interpretation as we would like to. For instance, a very simple example is a torus. So how do we incorporate the geometry of a torus? We just say that we need two transition maps. One transition map goes around one circle connecting the dots for each dot, and the other transition map goes around the other circle. So right, a torus can be generated by a bigger circle and then a smaller one. And so with these two transition maps in each point of the mesh of the torus, you can be translated along like parallel axis or meridional axis. And so this actually gives you the structure of any surface in the space. So if you want to have three-dimensional volumes, you need three transition maps. Okay, so and it goes in besides the three dimensions, you want the expressiveness of moving forwards and backwards. You have these six transition maps as we have implemented in the temperature model, right? So the number of the transition maps in the link structure determines its complexity, and it's all a matter of how we interpret it. But the structure is the same, and this is important from the computational and mathematical formalism, is to have a definition which is stable. It is a set of indexes, a realization map into a space, and transition maps. And then with this information, we have an interpretation. Each specific instance has a very precise interpretation, and then that's where we take advantage of it by transporting this interpretation and translating it into the mathematical physical equations, like the heat temperature equation, or could be any other physical equation. Because we have volumes, we have cross-section areas, that can be added as parameters to each indexing point in our structure. This is what is the key idea.
And right at the beginning, so the last question or comment is right at the beginning, you rather grandly, I think, but not very usefully, introduced the idea that we could print an atom. And
Yes.
I think, do you not think that it would be helpful, because you talked about using this methodology for talking about thermal conductivity, but thermal conductivity has a length scale because it depends upon the phonon wavelength, or however else you might think of. It's a macroscopic property. It's not a microscopic property, and therefore if you made your model so you only had 3 atoms, talking about the thermal conductivity would be meaningless. You would have to think about a different way of doing it, and it's a simple way of providing a length scale.
That's right, and
that is practical, because I think it's good to sort of have a universal or grand idea, but also it needs to be in the sphere that people can make use of it. And for example, there's very few places in the universe where you could print an atom, and so it wouldn't be universal in that sense, because it'd have to be cold enough. And there's very few places in the universe that are cold enough, other than in a few laboratories in the Western world.
Right.
So to print an atom at a point requires additional constraints, more than you're describing, and therefore it sort of perhaps renders the usefulness of everything else you're talking about.
Of course, but the point is that we have to, since we are trying to arrive to a definition, we have to consider all possible aspects of it and try and test it against everything which we can conceive of. And one of the applications that we have in mind is that the notion of this notion of multilink can actually be used to model one atom. So in the sense that, in the same way as I was saying, we can have one point and then these parameters on top of it, like a number of, like a polygonal shape with some sizes and some radius. This can be transferred into an atom as with its orbits, electrons as orbits, in which energy, state of energy is it in, etc. So it's again a parameterization. And so I suppose the next talk, Stelina, will also talk about this fundamental, more level fundamental at the level of atoms. And so what we are trying to do is actually to model different scales with this structure, and saying that, okay, some things are parameters, some other things has to be put in as geometry, and something else is living on the stage. So there are these 3 levels of the stage where things are being put in, the indexes of how many things are we considering in, and the relationships between the things.
Yeah, okay. Any final comments or questions? Okay, thank you very much, Nelson.
Thank
and
you.
we move on to the next talk, which is from Estelina Silva.
Yes, thank you.
Hi there.
Hi.
Thank you for being here. And you're going to talk about beta arsenic 2 tellurium 3 pressure-induced 3D Dirac semimetals. So we look forward to that. Thank you.
Okay, thank you. So I've got disabled the screen sharing.
So if you move the mouse towards the bottom of the screen, a series of buttons will come up.
Yeah, now it's no, but it was disabled. Yeah, it was.
So Thomas?
It's enabled now.
Now it's enabled. Thank you. Thank you. Thank you. Thank you. Okay. So first of all, thank you for inviting me. My talk will be slightly different than all the talks that were really directed to the universal printer. However, I'm going to try and link the studies that I do. Like Nelson said, I do mostly atomistic studies, studying electronic properties and phonon properties of materials, mostly phase transitions when you apply pressure. Because you can enable other structural phases and obtain properties which are completely different than those systems that are well known and whose properties are, and if you compare these properties with those at room conditions, completely different. So I'm from the University of Porto, first of all. Yeah, and so my background is physics, material science, mostly doing simulations and computational modelings. So first of all, in order to relate to the topics to the printers, to the 3D printers, I'm just going to talk a bit about graphene systems, which is, well, I hope well known to the majority of people. And it's an amazing system because in 2004, the system, two Russian people, but at the University of Manchester, they managed to, well, not synthesize, but with a sellotape, using graphite, they managed to get a monolayer sheet of carbon atoms. Stable, and managed to obtain this as a stable system. So graphene can be seen as an allotrope of carbon, of graphite and diamonds. Or however, it's different symmetries, so it's a different hybridization of atoms, which is the sp2. Graphene, however, became a boom at the time, 2004, because it's a system with completely different properties than conventional semiconductors, mainly because of the electronic properties. So if we look down here, we can see that so the linear dispersion is linear, which enable ballistic properties of the charge carriers, which is, and it's different than a conventional semiconductor, which is mostly these bands, or which describe the dynamics of the charge carriers, are mostly parabolic, and these would enable some effective masses of the charge carriers, making them heavier, and it affects the velocities of these charge carriers. While in graphene, you have linear properties, making them like a massless charge carriers. Okay. So I already spoke about the properties. Another amazing property of graphene is that it's very strong. It's got high resistance, even stronger than diamonds itself, actually. Also, graphene nowadays is being considered for several applications, as in batteries, for buildings as well, biosensors, and like Professor Geoffrey in the morning spoke about bioimplants. It's also been considered for such because it's a biocompatible material. Yeah. That's interesting. The paper, a very recent paper that came out just before Christmas, that shows about the printing of biological implants, which is using graphene as ink of the printer to do this, to these biological implants, which is quite amazing as well. And it's a novelty that everyone is now also working on these in graphene for this kind of applications. I have just a video here, if anyone is interested. I took it from the physics science website that's related to the paper, that they show how they do this printing of the, but you guys probably know this better than me about the functioning of the printers. but
So at the
they
moment,
are.
we can only see the top bar of your
Oh,
presentation.
sorry. You can't see any.
Yes, I think you need to probably select the full screen.
No, actually I can see it.
I can see it
Can
too.
you?
Yes,
Yeah,
I can
it's
see the
fine.
video.
Yeah.
Oh,
Okay, so yeah, probably some. Yeah, so this just shows the printing of these. Okay, sorry.
all right, that's better. So I've
Yeah, sorry about that. So it's just, it shows the printing of the array of electrodes using graphene as the ink. And these have been implemented in actually in mouses' brains in order to study the synapses of the brain. Well, yeah. And so this also paper came out very recently. It's also also based on graphene, but it's using, so it's mostly a review that speaks about the tissue engineering with the printing using the 3D printers, which is quite amazing. And now it's a field that's also a very, people are really going into these fields. Yeah, okay, this is another paper that came out also that really shows that graphene aerogel ink for the printing as well, which are, okay, I'm not going, I'll just leave the links if anyone is interested in to look it up, so on, okay. So why did I speak about graphene? Because of its properties, like I said, the linear dispersion of that you see, that it gives the electrons or the charge carriers and amazing properties which you don't find in normal materials. Nowadays, there are other materials other than graphene, which people are starting to look at, and which are in the 3D dimension, because graphene is just a sheet, a 2D dimension system. And however, by looking at certain systems which have a specific space group, so in the rhombohedral symmetry, you can already find 3D systems which also present these Dirac cones, or the linear dispersion, in which you have the valence band and conduction band which touch at the Fermi level, which gives you a semi-metal properties in your system. So nowadays you can already find 3D systems. You have to look it. And in this case, what I'm going to show is that by inducing pressure in the system, you can induce quantum topological phase transition, inducing a Dirac semi-metal. Or another interest in these systems is that they show two amazing properties, which are topological insulators, and they are also potential candidates for thermoelectrics. Okay, so just to give a small showing of how people now are also moving towards the studying of these potential 3D Dirac semi-metals, and looking at these systems are at the same time topological insulators. This means that at the bulk, they are insulators, but they have surface states which are symmetry protected, and they are conducting. Like in the slide I showed, so in the green, you see it's the bulk states which are insulators, but the blue lines here are surface states which conduct the electrons. And that's therefore that these are the conventional topological insulators. One of the first that were found was the Bismuth Telluride a few years back. And people were quite amazed because 3D systems with these kind of properties were a novelty at the time. The interest is also now, since topological insulators, one of the characteristics is having heavier atoms and small band gaps. These are also the same features as a good efficient thermoelectric material. Therefore, the interest in studying systems which can have actually these two properties for these kind of systems, okay? A thermoelectric, as you probably all know, you can generate from heat, you generate electricity from the heat, yeah, because of the flows of the electrons across a temperature gradient. To have a good thermoelectric, you have to look at some properties, but mainly for atomistic calculations, we look mostly at the lattice thermal conductivity to see the behavior of the phonon properties, and the goal is to get a low enough lattice thermal conductivity in order to enable a high temperature gradient from both sides of the system. Yeah. Okay, just to show you this, I found this this figure very interesting, and that's why I put it here. It's just to show the difference of the different gaps for the different systems, which, for example, this would be an insulator or a semiconductor, depending on the width of the gap. And then you have this Dirac semi-metal, like I showed in the graphene, in which the conduction band the valence band and conduction band touch at only one point at the Fermi level. This is a semi-metal. And then you have a topological insulator, in which you have the bulk states are insulating. However, the surface states would enable the conduction of electrons, and they are topologically protected. Okay, I'm not going to enter into the specifics of the codes that I use, nor the theory. Otherwise, I would need another talk to do that. I'm just going to give, I'm just going to say that, okay, the calculations are done at an atomistic level. The electronic properties are based in a theory, which is the density functional theory, in which you consider density to get the ground states properties of your system. However, also I used a many-body perturbation theory, because density functional theory has a problem when describing band gap widths because of okay, some exchange correlation functionals which underestimate the gap widths, and therefore you can use the picture of the green functions or the many-body perturbation theory in order to try and get a more realistic band gap when you try to compare with experimental data. Yeah, for the phonon properties, it's lattice dynamics that you use, and then you use the density functional theory as because you have to compute to get the vibrational properties, you have to compute the interatomic force constants between the atoms, because these atoms vibrate in equilibrium, and so you need to calculate these forces, and therefore you really need to have your systems very well converged electronically in order to get these kind of properties. Lattice thermal conductivity is the same. However, you have higher order for higher order terms in order to obtain anharmonic properties. And these are phonon-phonon interactions, so it's heavier calculations, while the lattice dynamics, when you do a Taylor expansion of your potential as a function of your positions of the atoms, you truncate the expansion into second term, and that's why you use the most simplest approximation, which is the harmonic approximation. Sorry, the harmonic approximation, in order to try and consider entropy for your system. Yeah. Okay, these are just the codes I used. Then, if anyone then has questions regarding this, I can explain a bit more. But I'll continue. I think people would be more interested to see the properties than the specifics of the theory, anyway. So. Okay, this is just the system like I showed before. So the system, this Bismuth Telluride system, is a rhombohedral system, and it's represented hexagonally. So you can see that between I don't know, can you see the mouse that I'm pointing? Yeah, so, yes, so you can see that it's a layered material. So between these big layers, these are you can consider it as being van der Waals interactions. So it's a layered material. So if you apply even if it isotropic pressure, you can think that you would have a lot of variations along the z-axis because it's a layered system. Yeah. Okay, so I just want to show the interest here, which is the electronic band structure, which are done for different pressure points at room conditions. So this would be our valence band, and the red is the valence band, which are contributions of the arsenium elements, and the valence band are the tellurium elements. So you can see that we this would be our Fermi line. We have semiconductor at room condition. Yeah, although it's not a very big gap semiconductor, it's smaller than 1 eV. It has a band gap. If we increase pressure to 2 gigapascal, an interesting feature occurs here at this gamma point. You get a limit. So we have here a similar feature as graphene, which is a Dirac cone with a Dirac point, because the valence and conduction band are touching at the Fermi level. Further increasing the pressure at 4 gigapascal, you see that the gap reopens again, which is interesting how pressure can change a lot. Not only the gap size, but also the character of the gap, because at 0 gigapascal, we have the top of the valence band is not at the same direction as the minimum of the conduction band. This is called the indirect gap semiconductor. While at 2 gigapascal, you see that the gap changes to the gamma points, which is the zone center, and it's a direct semi-metal, direct gap semi-metal. Yeah. So yeah, it's just a zoom of the 2 gigapascal system that I showed before. So yeah, we can clearly see so a Dirac cone, and this is what they call a prototypical graphene system, which large spin orbit coupling, in which the valence and the conduction bands touch at the Fermi level. So this would be what we call the pressure-induced quantum topological phase transition. Okay, this is just a plot of, because on further applying pressure to the system up to 12 gigapascal, what we see is that the gap, like I said, at 4 gigapascal, the gap reopens again, but then it starts to decrease once again. And slightly over 6 gigapascal, we have another transition, which is a transition to metal, insulated to metal, because we will see, yeah, this is an example of a 7 gigapascal system. So the valence band will be at a higher energy than the bottom of the conduction band. Yeah, so you represent these as a negative band gap because it's changed the position with reference to the Fermi level. Okay, this is just a table, what I said before, just to show the character that we have all indirect band gaps. However, at 2 gigapascal, it's direct as a Dirac cone. Another interesting feature we tried to study was to see if we in fact have a topological insulator. And so we done a topological analysis of the eigenvalues at different isometry K points in momentum space. And so we analyzed these topological features. And for what we saw that from 2 gigapascal onwards, we do have a topological insulator. However, at 2 gigapascal, it would be a topological insulator, topological Dirac semi-metal, yeah, which is quite interesting because that's what we were aiming for, actually. So now going away from the electronic properties, but going to see the vibrational properties of the system. So in order to see if a system is actually dynamically stable or not, in other words, if experimentally you can synthesize the system in a lab, we really need to look at the phonon properties. If the system is not dynamically stable, you will have some frequencies which are imaginary and represented as negative frequencies. And this is an indicative that your system, at the conditions that you're considering, does not exist. So we were looking at the phonon properties for different pressure ranges as well. This one goes from 0 gigapascal up to 1 gigapascal. There was so at 0 gigapascal we see a slight instability there. So it's very small. So there's a small fraction of the mode that goes to negative, which represents a dynamical instability. However, it's very small, and this can be related with the theory that we are using, which is the harmonic approximation. Since the system is quite anharmonic, it could be due to the lack of anormosity that we are not describing, and therefore the small instability. Looking at the eigenvectors to check what vibration does this correspond to, we just see that by looking at the arsenium, so the green, the light green are the arsenium atoms, and what we see, it's mostly the breathing mode between the layers. So it's the arsenium that are trying to get further away, and this can be related to that instability. Okay. By considering higher pressures, we see that the instability disappears, and in fact, these frequencies get higher these modes get higher in frequency, which means that the system is getting stable. However, another curiosity, which I didn't, okay, I haven't got yet, but there was a slide that I'm missing, that we have to look a feature in the phonons, which is at the gamma point. Well, we can look here. At the gamma point, we have these modes, which are very low as well. These modes, it's not usual to find these dips at the gamma point and very low frequencies. If we just take two of these because these are related to two optical modes in which I plotted here for more clarity. We have here, so this would be IR active mode. And what we see is that for increasing pressures at around 1.5 gigapascal to 2, it's very, very low. And actually this is related to a Kohn anomaly, which is actually related to the electronic linear dispersion, or the Dirac cones. And this can anticipate that we will have a instability in the lattice, or we are in the proximity of instability. Now, going to the lattice thermal conductivities, which is what we were also interested to see, if you remember, if the system is a topological insulator, the interest is if it is also a good candidate for thermoelectric by looking at the lattice thermal conductivity. So what we see for the three different pressure points, so before the transition occurs, the transition of the Dirac point occurs, at the transition, and after the transition. What we look here is that at zero, I didn't put the 0 gigapascal because, as you saw before, there is a small instability, so it doesn't make sense. Because of these models, the negative modes will not be accounted for. So you should not do these calculations, or if you have dynamical instabilities. Therefore, at 0.5 gigapascal, since the system is already dynamically stable, the calculations was done from there onwards. Yeah. We tend to look at the lattice thermal conductivity at room temperature, 300 Kelvin, more or less. And these are the values that we obtain at 0.5 gigapascal. So these are very, apologies because I forgot to put the, oh, okay, I've got the units there because I was saying that I forgot to put the units. These are very low values. So 0.098 and along the layered direction, which is the Z, yeah, it's more lower, but that's normal to see because if you have a layered material, the thermal conductivity will be lower in that sense. However, the interest here is one of the first materials that was found with the very low lattice thermal conductivity was this cadmium arsenium, well, CD88, so cadmium arsenite. I think that's the name, I'm not sure, but it's CD3AS2, which was found to have the lowest lattice thermal conductivity around 0.3 to 0.7, okay? And actually we found a lower value in the sense. If we do the lattice thermal conductivity at the Dirac point, at the pressure point where we found the Dirac point, it increases. It increases slightly, however, it's still low compared to other systems that are good thermoelectrics like tin selenide, which have lower values around 2, more or less. The interesting also is at 4 gigapascal, the values really increase, but another interesting feature is that the values along the layered direction is getting similar to the in-plane direction, which is meaning is that the van der Waals, because of pressure, you are getting more probably more covalent like environment, and because the layers are getting closer to each other. Yeah, so with this I conclude with this conclusion which I already spoke of, and I will not repeat, but the getaway message would be that these 3D systems which are prototypes of the 2D graphene system can also be probably considered as also good candidates for probably ink printers to do bio implants. Probably in the future could be a potential applications for that as well. Who knows? So I acknowledge all these collaborators and colleagues that helped out with the work, and yeah, and of course for the computational resources that were needed to do these calculations. Okay, thank you very much for your attention.
Thank you very much. So now we have expand the screen. You're not socializing, Nelson, are you?
I was raising my hand.
To me.
I thought you were waving.
No, actually, I wanted to make a question, but I'm waiting for the opportunity.
Okay, I'm just trying to expand my. Okay, so we have some time for questions and comment. Nelson.
Yes. Okay. So first of all, thank you, Selina, for the nice presentation. It's really something. And I'm curious. So tell us about this simulations and computations. How much computational effort does it take to compute all the things?
Well, this was nearly a 2-year work for me. So the electronic structure, if you use simple density functional theory, at the lowest level, you can see that. It's not that heavy depending on the size of the system, because this system actually, the unit cell, you can represent the unit cell with 5 atoms because we use periodic boundary conditions plane waves, yeah? So
okay.
you can do the unit cell. However, if you go to many body theory, which is formulated from Green's functions, those are more heavy calculations, and they, depending on your systems as well. For this system, it was easy because it's a 5 atom. However, you do need a supercomputer to calculate, to do these calculations.
Yeah.
So for around, for each pressure point around, I don't know, 12 to 24 cores you would need to do the calculation. Yeah. For the phonons is more complicated because the phonons, again, this is a nice symmetry because you do not, it's a very symmetric symmetry. So to do the phonons, I use the finite displacement method. You need to calculate different symmetry inequivalent displacements. So for the system would be around 10 different configurations so that you calculate the false constants. From that, from the false constants is then where you get your phonon properties. The thermal conductivity, on the other hand, it's much more complicated because it's a 3rd order false constants. You need all the phonon-phonon interactions. So instead of the 2nd order, you have 10 displacement files for the system. For the thermal conductivity, you have around 700 displacement files to compute. Okay, it's only single point. You just need to calculate one iteration to get the electronics, to get the electronic energy and the force constants. But anyhow, 700, you really need a supercomputer with and put 700 calculations in the queue so that they can calculate. It's heavy calculations and not everyone. Nowadays, now with all these trace calls, European calls, and Portugal is also now with 3 supercomputers. Now we are actually luckier in that sense. And we can now on our own do these calculations. But since I had collaborations with both, because I done my PhD there, I used to use Archer, which is the UK supercomputer, and the Spanish one, Mar Nostrum, because I had been there as well, because in Portugal, it would be impossible to do this. But now, this year, it's already better, because now we fortunately already have some resources on us for our own, which is good.
Thank you.
Thanks.
When we think about simulations, we obviously gasp at the vast array of data that you're able to generate from the simulation. And I wanted to ask you about the challenges in experimental verification, because the experiments, I would imagine, very rarely reproduce the simulation, in the sense you're looking at a pure compound that's crystalline, that doesn't have any defects, no impurities or anything. And I wonder, because you're looking at a very, not delicate, but complex set of properties, how they're affected by the practicalities of people doing experiments and extracting out that data.
Yeah, well, thank you for the question, actually. So just to give a small background on this. So I started doing this system. I went to Spain 2018 with Marie Curie, and I was working directly with experimental groups. I was the only theoretician to do calculations to compare with their systems. They actually had synthesized some arsenium telluride systems there. However, so the phonons are mostly to compare with their Raman spectroscopy results. And actually at low pressure, we did not get any similarities. It was really, really bad. And they had to repeat, and they even asked to help with, I think, some people from Grenoble to synthesize again the system at that symmetry. And no one knew, because below 2 gigapascal, they could not actually get any viable results. However, above 2 gigapascal, for example, lattice, the structural parameters, lattice parameters, we look at volumes to compare as well with bulk modulus. It's a good way to compare if the systems are well, at least comparable, right? But yeah, it's not easy. And like you say, you can have impurities. One thing that they were thinking of, what was happening is that because it's a very low it has a very low gap, I think it burns out when they are doing Raman. It burns out at very low pressure, because above 2, then the gap increases again. So yeah, at this moment, they do not know, and we cannot compare below 2 gigapascal. However, above, we are getting reasonable results with the Raman coefficients, which I compare with so I didn't show you, but I had another slide, but it's not here. So at the gamma point, by looking at what we call, it's the zone center. So the Raman spectroscopy is the vibrations at this zone center. And so what we compare is the frequencies at this point, more or less, to compare with the Raman. So like I said, above 2 gigapascal, it was getting good consistency. For the lattice thermal conductivity, that's more complicated, because there have been some studies and they were thinking on doing some thermal conductivity, but only at 0 gigapascal, because I think it's not easy to do an experimental apparatus with pressure and lattice thermal conductivity. Only very, very few groups manage. Actually, there is a PhD student which I'm co-supervising. He's an experimentalist, but also interested in doing some calculations. So he's doing some calculations to compare as well. He was going off to Israel, because I think, I don't know which city, but I know there was a group that managed to do thermal conductivity with pressure, actually. Pressure and temperature, actually, because they were looking mostly for superconductivities as well. But with this COVID issue, he didn't manage to go, because he was going last year, and then, yeah, you're right. It's not very easy to compare, but we try to compare mostly the structural parameters. If they agree, then we can pursue other properties that experimentalists cannot observe, for example, and we can say, yeah, okay, the structural parameters are similar, so we think that this is what you should get, more or less. Yeah.
Thank you. Any other questions or comments? Right, so rather bizarrely, we've arrived at the close of the conference within a few minutes of the scheduled time. And now I ask Nelson to make a few summarizing remarks about the presentations made over the day. Over to you, Nelson.
Okay, thank you very much. So it is a great pleasure that I've heard all the talks of today. It has improved our common knowledge about the direction of where we want to proceed. This is somehow as I was saying in previously, we actually have a pretty much good idea of the direction that we want to follow, but of course it's always being able to small adjustments, and so this is to connect with the talk by Lau. So we will incorporate this interesting idea of at the same time as we are printing in our experiments that we are conducting here at the CDRSP, we will try as much as possible to measure in real time what is being printed and use this as feedback loop alimentation to try to adjust in time the process of printing in order to make it as much as possible to match the design printing process. Then the other talks, I think, summing up the key ideas and contributions to the project of the universal printer, is that we can actually use these results made experimentally, whereas it is the inner structure of the filament in synchrotron analysis, or thermal properties of the materials, or methodologies developed to arrive at the right experimental tests, or developing software that can be used to cope with these simulations. But the essential idea in my perspective is that we can actually use this as a whole in order to improve our model. And so the model as we see it now is this multi-link structure that I've mentioned. So it is a well-defined mathematical structure which has the advantage of it can be tested against any possible outcome, any possible interpretation that we can come up with it. So this part, I think, until it fails against some new conceptualization or experiment, it is stable. So we are happy with this notion of multi-link structure as modeling something to be printed, whereas the place where things are happening, the stage, this is not yet sure. So we can think of topological spaces, we can think of geometrical objects, metric spaces with different metrics, geodesics, and so on and so forth. But in the end, this will be concerned with the atomic level. I don't think that we can escape from that. And as Estelina was showing us, there is still much work to be done. It is not a matter of a couple of years, it may be a couple of decades that we will still have to continue pursuing these results. So to have better simulations, to have better computers with more computational power, and generating simulations more and more accurate, so that will allow us to make better and better predictions, which in the first place will allow us to make better and better design structures, so that we will have a more precise control of the printing process. And I think this is pretty much what I want to say.
Okay, thank you very much, Nelson. I remind all of those still listening that there is the opportunity, if you follow the link in the chat message of the first one of the day, to vote for the best, your opinion on the best presentation of the presentations today. I'd like to thank all of the participants and all of the speakers for making the first session in the International Manufacturing Forum series a good success. I remind you that this is a way to spend the first Thursday of every month of the year, and so the next one is it sharing? No.
Yes.
Yes. The next one on the 4th of February is concerned with COVID-19 and manufacturing. And we have a great array of speakers already, but I would emphasize that in every one of these one-day sessions on the first Thursday of each month, there are opportunities for oral presentations. And if you have something interesting to present, then please submit an abstract via the website. In this particular series, we're working on the principle to consider the abstracts as soon as they arrive. So your abstract will be considered in isolation. We won't wait for all of the abstracts to come for that particular session, so we will just accept it. So if you get in early, then you can claim one of those presentation slots. So